Hello! We discussed weak dominance last time. In this lecture, we will discuss a game with a weakly dominating strategy, and that is a type of auction. Let's first look at a general setup for an auction. A seller puts one item up for an auction. Potential buyers put in bids to buy the item. The seller decides who wins, usually the highest bidder, and the price they pay. There are many ways that auctions can be done, but when you think of a typical auction, they are usually open bid auctions. We think of potential buyers bid repeatedly until no one else bids. The seller will then sell the item to the last bidder who gave the highest bid, and they will pay their bid price. Now, this is a bit harder to model as a strategic game, since it involves a sequence of choices, while a strategic game involves only one choice for each player, and that choice is done simultaneously. Another type of auction that is easier to analyze is sealed bid auctions or closed bid auctions. This is where each buyer submits one secret bid to the seller, and the seller will look at the bids and decide the winner. Now, there are a few variations to closed bid auctions as well. One natural method is the first price auction, and that is the highest bid wins and the winner pays their bid. So if there are three bidders who bid 150, 100, and 200, then the one who bids 200 wins and pays 200 to the seller. Now, does this simulate an open auction? If we had the same three bidders in an open auction, would the winner pay 200 to the seller? And the answer is no. In the open auction setting, when the price goes up to 150, the winner will then bid slightly over 150 and win, as nobody else would bid higher. So they would actually pay around 150 instead of 200. So that leads to the idea of a second price auction. The highest bid still wins, but the winner pays the second highest bid. So in the case of the three bidders here, the one who bids 200 wins and pays the seller 150. And this simulates the idea of an open auction a bit better. We now analyze this auction. For the setup of our auction, we have potential buyers in the set N. Buyer I thinks the item has value Vi. This is their valuation. The item is worth this much to them. Now suppose buyer I submits the bid Bi, giving strategy profile B. The winner is the buyer who submits the highest bid and pays the price equal to the second highest bid. If there is a tie, then the winner is the buyer with the lowest index I among all tied buyers. So now, given a strategy profile B, all the bids from all the players, the utility for buyer I is Ui of B, which can be broken down into two cases. Either buyer I wins in this strategy profile B, or they don't. It is easy to see the utility when they don't win. They just get utility 0. They pay nothing and they win nothing. If the buyer does win, then their utility is what they value the item to be, which is Vi, minus what they pay, which is the max of Bj for all j not equal to I, the second highest bid among all the bids. Now, what would be the strategy to play this game? Suppose your valuation of the item is 100. Would you bid anything other than 100? Could you get higher utility by bidding something else? What we want to claim is that there is no benefit to bidding anything other than your own valuation of the item. We will analyze this through an example, and then write down the formal proof after that. We will break into two cases. In the first case, suppose that your bid wins and the other bids are shown here. The second highest bid is 75, so we will pay 75 and get a utility of 25. Now, can you see what would be the utility if we do not bid 100? Well, if we bid anything that is more than 75, we still win. We still pay 75 and we still get a utility of 25. But if we bid less than 75, then we will lose and our utility becomes 0. In the second case, suppose that our bid loses. Our utility would then be 0. Once again, can you see how the utility changes if we do not bid 100? We see that the highest bid is 121. So if we bid less than that, we still lose and the utility is still 0. However, if we bid more than 121, we win, but we would pay 121. Our utility is then minus 21. So in all cases, our utility does not increase if we bid anything other than 100. So bidding our own valuation of the item is the best possible play in this game. We now prove a slightly stronger result in this theorem. In the second price auction, VI is a weakly dominating strategy for player I. There are two things we need to show in this proof. We first show that the utility of playing VI is at least as good as the utility of playing anything else. We then show that there is a situation where this inequality is strict. We now show that playing VI gives us the highest possible utility. We will break into two cases. In the first case, suppose that VI is a winning bid in a strategy profile VI B-I. We let BJ be the second highest bid in this profile. This could equal to VI. Since VI is a winning bid, the utility for player I is VI minus BJ, which is at least 0. We now look at what happens if player I changes their bid to BI. There are two cases. If BI is greater than BJ, or if BI is equal to BJ and I is less than J, then BI is still the winning bid when we change our strategy to BI. The payment is still BJ, so the utility remains the same. Otherwise, BI is a losing bid, so the utility is 0. And this is at most the utility of playing VI because that utility is at least 0. So the utility of playing VI is at least the utility of playing anything else. In the second case, suppose that VI is a losing bid in our strategy profile VI B-I. We now let BJ be the winning bid, so BJ is at least VI. Since we have a losing bid, the utility for player I is 0. We now look at what happens if player I changes their bid to BI. Once again, there are two cases. If BI is less than BJ, or BI is equal to BJ and I is greater than J, then BI is still a losing bid. So the utility is still 0. Otherwise, BI is a winning bid, and the second highest bid becomes BJ. So the payment is BJ, and the utility is VI minus BJ. And this is at most 0 because we have the assumption that BJ is at least VI. And since the utility for playing VI is 0, playing BI has utility less than or equal to playing VI. So we can conclude that playing VI is at least as good as playing anything else in this second case. So, in both cases, bidding VI gives the highest possible utility among all possible bids for player I, and that completes the first part of this proof. To show weak dominance, we still need to show that for all the other bids BI, there is some situation S minus I such that the utility of playing VI is strictly greater than the utility of playing BI. Once again, there are two cases. We first suppose that our new bid BI is strictly less than VI. Can you think of a situation where the utility of playing VI is strictly greater than the utility of playing BI? We let k be a number that is greater than BI but less than VI. And we set bj to be k for all j not equal to I. This means that player I plays BI and all the other players play k, which is greater than BI. So when VI is played against B minus I, player I wins because VI is greater than k and pays k. The utility is then VI minus k, which is positive by assumption. On the other hand, when BI is played against B minus I, player I loses because BI is less than k, and the utility is 0. So the utility of playing VI is strictly greater than the utility of playing BI in this situation. For the second case, suppose that BI is strictly greater than VI. Can you find a situation where playing VI is strictly better than playing BI? We let k be a number that is greater than VI but less than BI. And we set bj to be k for all j not equal to I. When VI is played against B minus I, player I loses because VI is less than k, and the utility is 0. But when BI is played against B minus I, player I wins because BI is greater than k and pays k. The utility now is VI minus k, which is negative. So the utility of playing VI is strictly greater than the utility of playing BI. And therefore, playing VI is a weakly dominating strategy, and that completes our proof. Now, one of the nice things about this strategy is that the way we play this game does not depend on knowing how the other players value the item. So it is easy to play. Simply bid your valuation. Now, normally in strategic games, you should know all the information. But in this game, it has the special property that even if you don't know all the information, you can still play it perfectly. We will talk more about auctions later on when we look at mechanism design. Also, there are many other Nash equilibria in the second price auction. As an exercise, show the following is a Nash equilibrium. Suppose buyer 1 has the highest valuation, V1, and buyer 2 has the second highest valuation, V2. Then, the strategy profile where buyer 1 bids V2 and buyer 2 bids V1 and anyone else bids 0 is also a Nash equilibrium. In the next lecture, we will start talking about mixed strategies, where we play a game using a probability distribution.